Okay, welcome back everybody to the EOCP's 2021 conference. I do want to remind the participants we do have a survey for both day 1 and day 2, and we strongly recommend that you complete that survey. It's important to us to see what's working and what's not, so please take the time to do that. And there are prizes with the people that do submit those surveys, so that's a little incentive for you. We're on the wastewater stream on this presentation. We're going to start our second presentation. It's online condition monitoring, extending the value beyond maintenance. Our speaker is Carl Sheehan. Thank you. Shit. Spartan Controls. Carl is a technical specialist with Spartan Controls. He focuses on digital transformation technologies. Carl is passionate about improving his customers' business performance through the application and process of automation and reliability solutions, and has been solving his customers' challenges for over 25 years. Carl holds an electrical engineering degree from Lakehead University and a diploma of technology and process control and instrumentation from BCIT. Away from work, Carl can be found fly fishing, surfing, golfing, and coaching hockey. Sounds like a pretty good life. So I'd like to introduce you to Carl.
All right. Hello, everybody. Pleasure to be here. So thank you for the introduction. I have been working for Spartan Controls, as we said, for the last 25 years. Spartan is the provider of automation solutions from Emerson Process Management for all of Western Canada. As we talked about, focusing on digital transformation technologies, but very specifically around reliability and how can we apply technology to make our customers' assets more reliable. It's obviously a very pertinent topic these days. Heavy focus within the industrial environments around reducing energy consumption, reducing costs, but also maintaining uptime and reliability of their systems. So today I'm going to talk about a specific topic related to reliability, and that's online condition monitoring systems. See if we can get the presentation going here. There we go. Perfect. So the topic today is online condition monitoring systems, and specifically not just talking about condition monitoring systems, but how we can use the information from condition monitoring systems beyond what they are originally intended for, and therefore get much more value out of those systems. What we'll talk about is the fact that obviously those systems provide value just on their own, but if we can provide even more value, that's the focus of, I guess, what a lot of people today are referring to as digital transformation. So in essence, I guess one could argue this is a talk about digital transformation, but instead of using all these buzzwords that you hear today and getting very abstract about it, I just wanted to get very specific on some applications to sort of drive the point home. So let's see if we have a problem with the clicker here. Okay, try it now. Or maybe I just have to go manual. All right. There we go. Perfect. Okay. The presentation would have been a lot more boring if it was just me up here on the podium. So this is good. We're back live. So specifically what we're going to talk about today is why would we apply condition monitoring to rotating equipment. Condition monitoring is the technology that we can apply not just to rotating assets, but to static assets as well. But just want to kind of keep the conversation focused today on rotating assets. We'll talk about the different tiers of condition monitoring, and then we'll get into exactly how can we use the information from online condition monitoring systems outside of the original intention to deliver more value. So when we're talking about online condition monitoring systems, obviously it's within the context of reliability and trying to make the assets that are being monitored more reliable. As soon as we talk about reliability, we want to reference what you're seeing here, and that is the PF curve, or the potential failure to failure curve. So within the context of a rotating asset, let's think of something very simple like a motor driving a pump. So in that case, as soon as that assembly is built and installed and brand new, it's operating at 100% of its health, and that's what you see on the axis, on the y-axis there is the equipment health. So over a period of time, it'll operate at 100% health, and it'll work as efficiently as it can, in this case here, delivering flow. Now, because it's a mechanical system, at some point in its life, it is going to experience a mechanical failure, and that's when the clock starts that we're showing here. That's time 0 on our graph. So at time 0, there's now a fault that has developed within that asset. Because it's a mechanical system, it's not like a biological system that'll heal itself, that fault is only going to get worse and worse. And as that fault gets worse and worse, it'll eventually start to impact the ability of that asset to perform its function. So in this case, this function is moving water. Let's say it's a pump. So what will happen is that over a period of time, as the fault progresses, you're going to see the equipment health is going to degrade until finally it gets to the point where it no longer performs its function. That is what we call a functional failure. So at that time, the pump is no longer moving fluid. That's the time at which we now need to do something about it. So that means we've got to actually repair the pump. If we've got a standby, great, we can switch over to the standby and at least get the standby going, satisfy the process requirements, and then fix the failed pump. Or we have to fix that failed pump as quickly as we can because it may be causing some downtime in the process. Either way, as soon as we get to that point of a functional failure, we now have to repair that asset. And that's when all the work begins. So we have to do the planning, have to order the parts, have to get the tradespeople organized, and then once all those planning activities are done, we then actually affect the repair. So all those activities occur at that point of failure. And that's what we call reactive maintenance. We run the asset, in this case a pump, until it fails, and then once it fails, the maintenance team gets out there and replaces the pump as quickly as it can. Like we were saying, if you've got a redundant pump, maybe it doesn't impact the overall operation. But if you don't have a redundant pump, okay, now maybe there's some downtime in our plant or in our process that, may increase the cost of operating that plant. So the whole idea here now with an online condition monitoring program or different online condition monitoring techniques is, instead of waiting for the asset to fail to figure out what that fault condition was, we can detect that fault condition much earlier in the life of the asset so that we know prior to the asset actually failing that there is a fault, what that fault is, and then we can start doing all those planning activities associated with the repair. So that's what we call moving from a reactive maintenance program to a predictive maintenance program. So with this type of technology, we can detect that fault condition online, and as you see here, we can move all those planning activities much further ahead. Instead of waiting for that asset to fail, we can get all the parts organized, we can get the tradespeople organized, we can coordinate with operations of when a good time would be for us to take that pump down so we can actually do the repair. And then at some point we have to physically shut that pump off and do the repair. So there's always going to be that downtime associated with the repair. We can't get around that. But what we can do is we can move all those planning activities further ahead in the cycle so that we're doing those while the asset is still running, therefore minimizing the entire downtime associated with that failure. So that's sort of been the traditional means of using these condition monitoring systems. It's how can we streamline our maintenance practices so that we're only taking the amount of downtime that we need, but also streamlining, just making things more efficient. Instead of having to order parts and then maybe we're going to be overpaying for those parts because we have to get them in a rush, or maybe we have to extend the downtime because the part delivery was too long, or maybe we have to keep those parts in inventory, which costs us money, just in this eventuality is to make sure we actually have those parts. If instead we can do all that planning while the asset is still running and still working reasonably well. We can save a lot of maintenance costs with our organization. So that's been the traditional means or the traditional motivation behind using online condition monitoring systems. Now, maybe some of the other things that maybe we didn't think about is what is the impact of performance on that pump? As we showed that as that fault increases, the actual equipment health and therefore efficiency of that pump is going to decrease. It's not going to be able to move as much fluid for the same speed. A lot of applications, we've got VFDs that are maintaining flow through the system. So as that pump starts to degrade, as its efficiency starts to degrade, that VFD needs to compensate by increasing the speed of that pump and therefore using more electricity. So we've got a lot of these applications, particularly on large horsepower motors, let's say, and large pumps, where we're going to be consuming much more electricity or energy because of that decrease in equipment health due to that fault. So again, we don't want to let that equipment degrade to that point where we've got a functional failure, because not only is it a high maintenance cost, it's also a potentially high energy cost. And of course, that's a significant focus today. So you see here on the curve, if we can do that repair further ahead, it's going to cost us less in energy consumption than if we wait till that we get closer to that functional failure point. From an overall energy consumption point of view, I've thrown some stats here from the city of Dallas. It's a fairly interesting slide that we use quite frequently that shows you that for a municipality like Dallas, when you take a look at of all the services that the city of Dallas provides, 59% of the energy is consumed in the water and wastewater systems. So these are the systems that are are significantly large energy consumers. So we're constantly focused, and we're seeing this focus now in industry, is more focused by municipalities on making their systems much more efficient. And again, condition monitoring systems are a potential way of doing that. Other considerations we have to think about, safety considerations. Again, if we are now doing the repair while the asset is down, the rest of the plant may be running, so there could be some other hazards associated with that, may be occurring after hours. So you've had some tradespeople that have worked a long day and now they're tired and having to do work. So there's all sorts of potential safety implications. If we can organize that repair with the operations during a normal shutdown, okay, now the plant is in a safe point. We're doing the shutdown, we're doing a repair during a shutdown, so it's a much safer environment. We've got all the proper tools and such in place that we need. From an environmental perspective, we talked about the decrease in electricity consumption. Here in BC, we're fortunate in that the vast majority of our electricity comes from hydro, but not a lot of municipalities can say that. So if you're taking energy from fossil fuel, again, if we can decrease the amount of energy that we're consuming in our water wastewater system, that's going to help the environment. Then there's also the customer service. Like at the end of the day, we are here to provide a service to our customers, right? They need clean water, they need lots of water, and they need clean wastewater. So it's our job to produce those. So anything that will impact the ability for us to meet those customer service targets reflects badly on us. We've got tax-paying customers that want to see their money spent wisely. They don't like to see disruptions in their service. So if we can be doing things to prevent those disruptions, that's just better for everybody overall. So there's all sorts of other implications or reasons why we would want to use online condition monitoring systems. So now we'll get into sort of the different tiers of online condition monitoring, or I guess condition monitoring itself. I keep saying online, we're going to get to online. We'll talk about different ways that we can do condition monitoring, and then we'll shift the focus strictly to online condition monitoring. So if we go back now to that PF curve, and we'll kind of take a look at the different technologies associated with condition monitoring, we have that, fault progress to the point where we get the failure. Well, obviously we can do nothing, right? We can just stay in that reactionary mode, wait for the asset to fail, and then fix it as quickly as we can, right? That's the do nothing approach. What we are seeing a lot of people do now is that we can install, 4 to 20 milliamp overall vibration transmitters on the asset. So at least now we're measuring vibration, and vibration is a very good indication of the asset health. As soon as we start to get a fault, what will happen is that the vibration that we measure on the asset will increase and eventually increase at a point where the asset fails, the vibration goes up. So at least by monitoring that vibration, bringing that information into our SCADA system or to our PLC or whatnot, at least we get some warning that, hey, something is happening with that pump. we need to get ready to do a repair on it. So we are seeing that's a very low cost way of doing some condition monitoring on the asset. The only downside to that is that it doesn't give us a whole lot of time. Okay, it's certainly better than nothing, and it's a good cheap alternative, but does it give us enough time to get all the parts ordered and give us time to get all the tradespeople organized? Maybe. Maybe it gives us days, but is it going to give us weeks? Is it going to give us months? Probably not. So it's better than nothing. It's certainly going to prevent a catastrophic failure, but there are other technologies that we can use that are actually better. Route-based vibration analysis. So this is a type of technology where a vibration analyst will come up with a portable analyzer. While the asset is running, they'll take different vibration measurements at different point in that asset, and they'll interpret the results of those vibration measurements to determine if there is a specific fault. That's a trade unto itself. These are trained professionals that know how to interpret that vibration signal and whatnot. But by doing those services, they can see with even much more lead time that there is a fault in the asset. So vibration is a route-based vibration analysis. It's a manual service. Like I said, it requires a technician to go around in the field. What you need to be careful with the route base is how frequently are you doing it, right? There's a lot of cases, let's say, where you may only be scheduling that service once a quarter. Well, a lot can potentially happen in the space of 1 quarter. It could be that, the last time they were out, the asset was perfect, but before the analyst can come out and do some more measurements or do another analysis, the asset could have failed. That whole PF curve could have occurred in between visits. So you need to make sure that the frequency of your vibration analysis program is fast enough that you can actually detect and fix those failures. And that's really the benefit that an online condition monitoring system will give you. It basically gives you that analyst that would come out on an infrequent basis, say every few months, where an online monitoring system will give you that information immediately, like second by second. And then we interface those online condition monitoring systems to our SCADA systems and our PLCs and whatnot, so we can actually get alarms in real time that indicate that a fault condition has occurred. So online condition monitoring uses the same technology around vibration analysis, but it just does it 24/7, 7 days a week, and gives us data on a second-by-second basis, so much higher fidelity. Now what we're seeing is this next shift in the progression, the technology going even further up that curve, and that's by incorporating analytics. So the idea is that if we can start bringing this information in, we can start doing some machine learning and different artificial intelligence algorithms and whatnot, correlate the vibration data to maybe some other process data that's going on, take a look at some root cause analysis. There's all sorts of techniques that are being employed now, but the idea is that as we get more information on these systems, we can actually do some analytics to detect those failures even sooner. So the whole push in the technology is how soon can we detect that failure, because the more lead time we have, the more efficient we'll be, and the decrease or the less our maintenance costs should be. So those are the various tiers of condition monitoring. Just want to make sure we're on the same frequency there. What we're going to kind of shift gears and focus on more now for the rest of the conversation is going to be those online condition monitoring systems, because those are much more prevalent. Analytics, it's definitely growing, but the technology is still in the early stages. It's getting better. It's going to improve over the next few years here, but right now online monitoring systems are much more prevalent out in the process industries. So when we talk about an online condition monitoring system, let's first of all make sure that we understand exactly what that system is comprised of. So as we said, the goal is to continuously assess the health of the asset in real time, and then alert us when that asset health is not 100%. So basically we have a system that consists of sensors that are installed on the asset. So the most common type of sensor would be your accelerometer to measure vibration or velocity or whatnot. So we'll put those sensors at different locations on the pump and the motor in this case here, and then we'll wire those sensors back into a condition or a data acquisition hardware platform, right? Typically a rack mounted system that's got like a control processor and some I/O processors and such on it. You see the picture, so they'll be contained in a cabinet out in the field. So you see the wires from the sensors will be wired to the terminal blocks on this data acquisition system, and it'll sit out in the box, out in the process area. Then layered on top of that, we'll have an interface from that data acquisition hardware to proper dedicated software applications that analysts can use to interpret the results. So the data acquisition hardware converts the raw measurements from those signals into usable vibration measurements, and then the analysts will use that data with their software application to interpret exactly what the fault condition is. Do we have a bearing fault? Is it an alignment fault? Is it a looseness fault? All these different things can be interpreted by looking at that data. So that, when we say an online condition monitoring system, this is what we're talking about, right? That whole system of sensors, data acquisition hardware, and then the software associated with it. Now, as we said, this has very strong and obvious maintenance implications. So typically it's our maintenance and reliability teams that look after these types of systems. They have to know how to look after the system. They have to know how to interpret the data. So these are dedicated professionals within that maintenance silos. We're going to talk about it here, but within that maintenance profession, they're the ones that would typically look at this information. So when we take a look at our organization, you know, in this case here, we're looking after the maintenance and the asset health kind of silo. We've got other similar silos. If you take a look at your organization, you're going to have folks that focus on the SCADA system and look after SCADA systems. You're going to have folks that look after your control systems and PLCs, DCS and such. You're going to have your technicians that do all the water quality analysis. So within the process industry and within our organizations, we're going to have these dedicated silos of specialists, right? And this is a good thing because these are people that focus on what they know how to do. These are dedicated professionals using dedicated equipment, dedicated applications, so they're good at what they're doing. It's a very efficient way to run the organization. But what we're talking about today, and the real crux of today's discussion, is everybody is focused within their own silo. But there's no reason why the information from these systems cannot be used outside that silo. And that's really what we want to talk about here today. So here we're talking about online condition monitoring systems within the context of that maintenance silo. Well, what happens if I can implement a system in my organization that connects the dots between all of these silos, and I can bring information from all those separate silos into one consolidated data layer, be it an historian or a data lake or however you want to do it. But the idea is that we consolidate and move all that data into one repository, and then on top of that, we can build applications that can use even more or drive even more value from that information. So we can be implementing analytics to do better prediction of fault detection. And that's what we're going to talk about here today a little bit. You know, there's some data visualization stuff. So there's multiple applications. Once we've built up that infrastructure, that can start leveraging that information and getting even more value out of it. And the specific application I'm going to talk about today is going to be what we call a energy management information system. Okay, that's the last time I'm going to say that. It's an EMIS, right? So energy management information system, EMIS. So the whole idea of an EMIS is that it provides in real time insights to the energy consumption within our organization. It can be used by the operations people to make real time decisions. Maybe they do have that pump that's consuming high energy. Maybe they can switch to a different pump that's not consuming as much energy. From an analytical point of view, it can be used for analysis of our process efficiencies, right? Maybe our process engineers can determine in real time that we have some process inefficiencies, and then maybe they can figure out ways to make our process more efficient or figure out the root cause of those inefficiencies. It can be also used from a strategic point of view from a corporate level, that maybe it drives us to implement certain capital projects, right? Maybe the process engineers identify an opportunity where we can make the process more efficient if we use different technology, or if we change the process, or we invest in certain capital. Well, from a strategic point of view, we would then use that as a justification to maybe implement one of these projects. So the whole idea then is an energy management information system, and EMIS gives us the insight of our energy consumption to allow us to make our organizations that much more efficient. And if you're to take a look at what Natural Resources Canada estimates, by implementing an EMIS, you can reduce your organization's energy consumption by between 5 and 10%, just by knowing in real time and reacting to your energy consumption in the system. So when we break down how an EMIS actually works and the functionality around the EMIS, what we do is when we implement an EMIS, we take all this energy data that we've collected on our process, and then based on that energy consumption data, we'll build these models. And what the models do is that they predict in real time what our energy consumption will be. And then these models don't just look at the energy consumption, they also look at the energy drivers. So are we increasing our production rates? Is it based on the time of year, right? During the winter months, we may be consuming more energy than during the summer months. So all of those different factors that would affect energy consumption are all incorporated into those models. And we break those models down on a compartmentalized basis so we can focus on specific process areas. Maybe we look at models for individual pump stations. Maybe we look at models for individual areas of our wastewater facility. The idea is that we break the models down in real time based on a certain unit operation so that we can isolate very clearly where the energy consumption is. So that first step is the sort of analytics that go into building those energy models. Now, once we've got those energy models up and running in the EMIS application, the next thing that we do is that we compare it to real-time measurements of our energy consumption. So we see where we should be operating and then where are we actually operating. And then based on that, if we are consuming more energy than our model says we should be consuming, we'll then produce an event to the technical people that can deal with it, or the operations people, or the maintenance people. But the idea is that we get that information out to the organization that says, hey, we are consuming more energy in the filtration area than we should be. And then that spurs action. Then people will go out and then maybe they'll use some of the other tools in EMIS to try to troubleshoot the problem, or maybe they have to go and do field inspections, maybe they can look at other historical data. But the idea, and this is the whole kind of crux behind an EMIS, is that it gives you that insight to let you know in real time that you are consuming more energy than you need to, and gives you the chance to go out and fix it. That's the value of the EMIS. Now, what I just described was the traditional method, the ISO 50001 standard way that an EMIS is implemented. It tells you in real time if you've got high energy consumption, gives you some basic troubleshooting tools, but that's about it. It then becomes a manual process by technical people, engineers, operators, whomever, to determine what is the cause of that high energy consumption and how can I fix it. So some of the tools that we'll use, for instance, would be your dashboard. So you see in the top right-hand side there an example. You may have your wastewater facility broken down into specific areas like primary treatment, secondary treatment, advanced treatment, and so on. And then for each of those areas, we'll say, well, what is the energy consumption? And in this case here, it's showing us that the advanced treatment has been flagged as consuming 8% more energy than it normally could. We can also extend this. We're showing you electricity right now, but once the EMIS is built, we can take a look at other energy streams, right? Do we want to measure what our overall freshwater makeup costs are? Do we want to take a look at what our chemical consumption is, right? So we can look at different energy flows within the organization, but because electricity is such a key component and like the main energy source that we use, that's what I'm going to highlight here today. So we get these dashboards that in real time alert us to high energy consumption events. There's also other tools in there like a cumulative sum. That's basically, it's just that, it's a running total of that difference between our actual energy consumption and our target energy consumption. And we're looking for those inflection points. So as you can see on that graph on the lower right hand side, that green trend, there's an inflection point at around like the 7th period that shows us at that point there our energy consumption or our target energy consumption was much higher, which gave us that negative trend. So we know at that inflection point, that's when it began. So now we can go back in history at that same time where we see that inflection point to try to troubleshoot and figure out what happened at that time to cause this high energy consumption. So those types of rudimentary tools are included in your standard EMIS. Now I'm going to show you some examples of where we've implemented EMISs. EMISs, never know how to do the plural of that. So in this case here, we had a filtration plant running an EMIS, and then it was flagged as having high energy consumption. And then when they went back and started doing some of the trends, they noticed that the red line is the actual energy consumption, and the blue line is the target energy consumption. So you can see where the motor fault in this application highlighted high energy consumption. So our energy consumption went high. And then after a period of time, by troubleshooting and whatnot, they went out and they replaced the motor and then brought the actual energy consumption back in line with the target energy consumption. So for that period of time, they were doing some troubleshooting to try to figure out what the actual problem was. Like I said, what we see on the plot here is just the energy consumption. But what they don't show you are the different contributors to that high energy consumption. So there's a period of time you can see where it's almost a full month where we are running at much higher energy consumption than we should have been, right? So one would obviously conclude that that's 1 month of lost opportunity. If we had gotten on that problem sooner, if we had solved that problem sooner, we would have saved a month of overconsumption. Here's another interesting example where we're looking at the energy consumption on a 4-pump system that maintains header pressure. In this case here, the way the control strategy was set up, they would bring on that 4th pump on an on-off basis as they needed that extra pressure. Well, what you'll see is that as the pressure decreases, they would turn on the 4th pump, and then once the pressure came above a certain point, they would turn that pump off. When you take a look at the target energy consumption versus actual energy consumption, you'll see again, every time they turned on that 4th pump, overall energy consumption required for that process would increase above the target and then come back down every time they turn it off. So over a number of these cycles, once it was identified by the EMIS, they then implemented a project where they were going to replace that 4th pump with a VFD. So now instead of running that pump at fixed speed at top speed, let's use a VFD to just run it exactly where it needs to run to satisfy the pressure demand and therefore save electricity. So again, another means where we're using an EMIS to sort of implement a capital project to make our system more energy efficient. Okay? So in all those cases, we're showing how an EMIS can be used to identify the high energy consumption event, but there's still potentially a lot of work involved by humans and whatnot to try to figure out why exactly is this happening, right? So now what we're seeing is the sort of next step in the evolution of EMIS is the incorporation of different analytic techniques. In this case here, root cause analysis. So what you'll see in the root cause analysis tree here, this is an example of a model that we've built. The way this has worked, if I go back a slide here, you'll see that at the very end on the far right hand side there, we have our actual symptom, right? So in this case here, it's the pump is showing poor performance. Well, if we go back one layer, that pump poor performance can be caused by mechanical damage, low discharge pressure, or high discharge temperature. So there's 3 separate conditions that can be causing that poor pump performance. And each of those conditions could have conditions that cause that. So you build this whole tree network of potential reasons why we're seeing low or poor pump performance. In this case here, it can all get linked back to that actual root cause. So if we follow this tree back here, the boxes are the conditions that are highlighted in red are the ones that are active. The ones that are in green are inactive. You can follow the red boxes all the way back and you can very quickly link your, sorry, I'm looking at it here because it's hard to see. You can see the poor pump performance going all the way back is actually caused by an oil filter clog on the pump. So instead of having technicians try to figure out what's going on and people troubleshooting in stages and whatnot, we can build these analytic models that will tell us in real time, like within minutes, that this is what's causing it, right? So you've got poor pump performance, you need to go out and change that oil filter, you need to clean the filter, whatnot. So instead of you having to do all the troubleshooting and spend hours potentially doing that, the root cause analysis analytics can give us this information in real time. Well, when we take a look at building those root cause analysis models, we look at traditional systems, right? So we're going to look at historian systems, we're going to look at DCS and PLC systems. These are what we're traditionally doing today in our organizations. That information is consolidated in historian, and that's what we're using to build these models. But what we're seeing here, and this is like one of the main crux of the conversation today, are things like online condition monitoring systems can also provide information that we can use in these root cause analysis analytics. These online condition monitoring systems are giving us very specific information about that asset that would not normally be in our historian. We're not going to bring in the fast Fourier transform of different frequencies of the vibration signal coming from this one point and then multiplying that by 12 points. There's so much information in these online condition monitoring systems that we just leave them alone, right? We don't bring that into our historian. But if we could get that information out, we can augment our analytics, like a root cause analysis analytics in this case, with that information to make the root cause analysis model even higher fidelity. So we can then incorporate, well, there's a problem with the pump because now you've got a bearing failure, or there's a problem with the pump because there's a misalignment issue, or there's a problem with the pump because it's got soft foot and it's wobbling around, it's loose, right? This is the type of information that we would not normally see. So now, bringing this back to the EMIS conversation is where our traditional EMIS was just giving us a quick, indication that we've got a fault condition. If we can start incorporating these root cause analysis models, we don't have to do the troubleshooting. the analytics will point us and tell us right away in real time, as you see here on the lower left-hand side, this is what your problem is. You are having a problem, you are getting high energy consumption, and that high energy consumption is being caused by this root cause. And as we demonstrated, that root cause can also be incorporating the information from our online condition monitoring systems. So we've taken the information from the online condition monitoring system, and now we've incorporated it into the analytics in our EMIS to make our EMIS even much more powerful. So now instead of waiting for that 1 month in that example that we showed we had a motor fault, we would have seen that we had a motor fault right away. We'd probably even see we had a motor fault before it started causing high energy consumption. But if we didn't fix it and it did start to lead to high energy consumption, we would have flagged that very quickly and then been able to organize the repair of that motor and then save 1 month of high energy consumption. So if you start taking a look at those events, you can very quickly justify the effort that it takes to stand these systems up. So I kind of went blasted through there. I'm going to kind of bring it all back here now. So essentially what we're talking about here, or what I've shown you today, is an example of where we can take that information from an online condition monitoring system. And if we can build up within our organization a means of pulling data from all those different silos and then consolidating that information, including information from online condition monitoring systems, we then give ourselves the opportunity to start building all of these higher value, higher level applications that can leverage that data. So the specific application I talked about today was an energy management information system. So that's one very specific way. There's probably other ways, I'm sure, within the organization that we can leverage that information to do more with it. We're also finding too that edge analytics in these devices, we talked about the potential for analytics. Instead of us having to do a lot of interpretation or build a lot of models, a lot of those are already built for us in the asset, or sorry, in the online condition monitoring system. So these systems are getting much smarter. They're performing the analytics on board. They're telling us what the fault conditions are. So we have to do even less work now to do the analysis on our side. And finally, we can use that information outside of our silo, right? The idea is that energy management information systems and whatnot can use that information to make their applications much more powerful. So that brings it to a wrap here. Got my contact information on there, Carl Sheehan. If you have any questions, you have my contact information, and please feel free to reach out.
Okay. Hang on, just got a question there?
Hey, so my question is, some of this stuff looks pretty expensive to implement. So what kind of minimum horsepower would you start looking at applying this stuff to?
Generally speaking, 75 horsepower. Right? Now that's traditional for like the big full-blown systems. We're seeing that come down now because these systems are becoming cheaper. 75 horsepower is sort of that make or break for a couple of reasons. One, it's what's the expense of the asset to replace that, right? And what's the impact? So usually 75 horsepower is your fairly general guideline. I've been watching so much politics. It's probably, you're getting a straight answer here today, right?
We got a couple questions. Here's
Sure.
a couple that were written down by one of the members of the audience.
All right, so with technology changing at high rates, what big shifts or changes do you see on the horizon? The biggest one I see, I alluded to it, was the incorporation of analytics right into the condition monitoring systems themselves. I showed you that traditional system where we bring the information into specialized software, and then an analyst will go through and do the analysis. So in a lot of cases, it's still very manual. What you're seeing now is that a lot of those analytics are being automated, so we don't need humans to actually do the interpretation. So the software applications themselves are using the analytics, and now we're seeing the analytics actually getting pushed down into the condition monitoring system itself. So now instead of sending just a bunch of vibration data to your SCADA or DCS or PLC that needs further interpretation, we're sending like health scores. We're saying like my bearing health is this, or my alignment is this. So people don't need to rely on, they don't need to rely on having an analyst interpret the results. They can get the results directly from the asset. So you're seeing much more of this type of shift in the technology. Oh, since you're such a hockey fan, does Canadian team make the run for Jack Eichel? I don't care if any Canadian team, as long as the Canucks don't. All right, we're good. We got to lock up PD and Quinn Hughes here, right? So never mind Eichel. It would be good to see him play maybe for the Montreal Canadiens. I don't know. That's my second favorite team in the NHL. Is net zero energy consumption realistic? If so, what systems are available? I think net zero energy is absolutely realistic. Technology exists either today or just knowing what we know about technology and how well and how quickly it builds upon itself. You know, being an engineer, I'm a huge believer and have faith in technology. So I just know that we will be able to get to net zero. This is the type of innovative type systems that we have to look at, and we have to be willing to sort of shift our thinking. We have to be able, or we have to keep our minds open. A lot of these net zero, I think one of the bigger, and we're getting a little political on it here, but a lot of it has to do with, I think, political will. It's that trade-off, right? You know, if you build it, they will come type of a thing. I think if we start investing in the technology, we can build upon the technology. I just think we need to be smart and strategic about how we invest in that technology. Like, it just needs to be very focused. We don't just want to have these big slush funds of money that's going to make us more efficient. I want to be, you know, specifically what are we doing with that money? But I think if we apply that money, the right technology, we can absolutely get to net zero.
For existing infrastructure, you know, is there a sort of a generation, say, of electrical VFDs that would fit this kind of thing, like, I don't know, 2000 and better or not? Because there's a lot of that information is coming back from the VFDs. You know, there would be no point in doing it on a VFD that doesn't have that information. So what is the sort of the rough year era of a VFD that would fit well with this program?
That's a good point. So you're looking at the actual VFD itself, and you're right. You know, if we take a look at older VFDs, maybe, you know, pre-2010 kind of a thing, you may not find a lot of the information that you may be looking for. Now, with that said, there's all sorts of pretty interesting things out there, like smart relays and whatnot, that they're not built into the VFD, but you can certainly connect them onto the VFD and the wiring coming from the VFD to the MCC and pull that information off. So just because you have an older VFD, I wouldn't use that to just disqualify, like, you know, oh, we need to upgrade the VFD, like maybe, or we can maybe just put one of these modules on there instead. So there is alternative technology outside the VFD where we could also address that.
So that leads to my second question is vibration monitor, for instance. Is that smart enough to tell you when it's the vibration monitor that's failing, or is it a
Yeah, so these systems, and again, that's just built into these devices now. It's part of the analytics. They don't just look at the data that they're measuring. They also they do the diagnostics on board to tell them what is the health. So do I have a bad IO?
Yeah.
If I've got bad IO, I'm basically going to ignore the information I'm getting from that IO point because I don't want to make any bad decisions based on that. So all those type of built-in hardware diagnostics are typically built into these systems.
So that would not necessarily go back to the EMIS system to determine that. That would be determined in the field by that particular instrument.
Well, actually, that's a really interesting point, because when we build these analytics, and part of what we need to understand about analytics, there's the analytics that you build in a lab in a university or whatever, and all things are good. It's all good data. And then there's analytics that you build based off data that comes from process industries. So as soon as you start building data from the process information coming from these systems, you have to build in these fail-safe mechanisms. You have to build in these error check mechanisms. Is the data that I'm getting good? Can I use this data to make a prediction? So we build that when we're building these models. There's all sorts of error checking and status checking. If we can get that status directly from the asset, and that speaks to other point about the data mobility. We're not just going to bring information on the measurement. We're going to bring a status. You know, is this measurement good? Can I use this measurement? And then we'll use that status when we're developing the model and doing our prediction. Or we may have to build some algorithms at the analytics level to interpret that's bad data or it's good data. Very simple example. I may be getting a current, and if that current is dead flat, I'll do a check to say that current is dead flat. That can't be right because current doesn't do that. It's always got some noise on it, right? Or if you see a sudden spike, it's like, okay, current just doesn't make a sudden spike. Maybe there's a short, or maybe there's something wrong with that measurement. So we put that type of fault detection, we build that into the analytics as much as we can.
So we have a couple from Zoom to go through. Can some of the analytical root cause data be provided by the manufacturer, or does it all have to be developed on site?
Oh, that's a great question, and you're absolutely right. Some manufacturers will actually produce their full FMEA failure mode effects analysis. They'll have it all broken down based on the components in that and how the information can generally fail. What they'll also do too, from a vibration point of view, is that they'll give you signatures. And they'll, you know, what we call it the graphic interpretation of the data. So it'll show you, if you see this, you know, if you see this certain frequency with high energy, it's this fault condition. Or if you see this frequency with high energy, it's this fault condition. So yes, some manufacturers will provide very detailed, some provide very little.
And then we have another one. Do any of these monitoring systems accept input from operator/maintenance teams? Say, for instance, analytics determines an imminent failure within the system. However, on inspection, it was determined that the prediction was incorrect. Improving the analytics learning, question mark?
Oh, no, that's, again, there's another topic for, that's next year's topic, is talking about operator-driven reliability programs. Like what you're talking about is exactly how some organizations build or use the data for analytics. They come from operators going out in the field with tablets, and while they're doing their rounds, they're filling out these tablets in very specific ways, and the information that's electronically captured now gets fed into the data lake, let's say, to perform the analytics. So we can either use data from those operators, or like you've mentioned, you know, you can build a dashboard, let's say, and the operator can put a manual override or some sort of information. Again, it's all about data, it's all about information. So as long as we give the operators means to get information into the system, once it's into the system, we can absolutely use it for analytics, right? So we may not have a temperature measurement, but maybe the operator says, you know, motor is hot to touch. Then that high motor temperature is used in our model, and we're seeing that today in the models that we build, absolutely.
Last one from Zoom. Can this integrate with various SCADA systems?
Yeah, so again, like we're saying this, like, you know, I'm talking about online condition monitoring systems in a general sense, right? You know, obviously our company produced them, but we're not the only ones. What you're seeing in industry are all of these systems from multiple manufacturers are adhering to open standard communication protocols, right? Modbus TCP, OPC UA, these are all open protocols, and they make all their information available. So that's what you're seeing is the interchangeability, and most modern SCADA systems can communicate using all of these standard protocols. And if they can't, there's all sorts of converter or protocol converters that can be put in between and such. So there's all sorts of technologies that we have either inherent in the device itself to communicate with open protocols, or conversion technology that we can use to interface it to any SCADA or PLC or DCS.
Okay, we got one last question, and I think you probably answered it a little bit, but I'll give you one last say on it. What's your opinion on the highest level examples or opportunities that these programs can present for us?
Probably like any app. What we talked about today was, okay, let's say an EMIS, and you get this information, and then, you know, the root cause analysis tells you that this is the problem, and you go out and you fix that problem, right? Well, anything that will actually close the loop and automate that. So it may not be from a maintenance point of view, you're not going to like send robots out to fix something, or, you know, maybe not today, maybe 50 years from now. But if you're making kind of real-time operational decisions based on that and closing the loop on that, that's about as high as you can go, because now you're automating the decision-making in real time, hopefully to make things more efficient, to make things quicker, but that's about the highest level. So, you know, things like real-time optimization systems, advanced process control, any of these type of applications that would actually close the loop, as we say, and perform actions based on information, that's as high as you can go.
Okay, well that wraps up from our time perspective, and I think we've got most of the questions asked. So on behalf of the EOCP, thank you very much for your presentation.
Awesome, thank you. Pleasure being here.
Yeah.
Go Canucks.
I'd like to remind everyone to take the opportunity to do the survey and submit that in. There are prizes for it, but more importantly, it will help us make the next one better.
or the next conference better. So your input is valued. We are going to break now for lunch. We will be back at 1. Have a good one.